Okay, so we are going to work on computing some degree measures, if they exist, using our inverse information. So remember, arctan or tangent to the -1 mean the exact same thing. And so our arctangent information was kind of in the middle of our handout right here on the back side. One thing that I kind of noted is that when we look at this, it's always nice to look at where we are going to be restricted, because over here in our inverse, we are going to have a restriction placed on us because our graphs keep repeating themselves. And so we are going to be restricted between -pi/2 and pi/2. If you think about the unit circle, which is on the chapter 5 handout, if we're talking about -pi/2 to pi/2, we're actually talking about down here all the way up. So this right half of the circle is what we are limited to when we are talking about our arctangent. And so I like to take a bunch of notes whenever I do this information so I can kind of keep stuff straight in my head. We are limited between -90 degrees and +90 degrees. That's the -pi/2 and the +pi/2. That's where theta has to live. So since we know this, what two quadrants do we know our arctangent has to lie in? Huh? Quad 1 and what? You said it, I think. Yeah, quad 1 and quad 4. So that's where we know we have to be. Now, remember, when we have theta equals arctangent of 1, we can rewrite this using regular tangent, right? We can write this as tangent of theta equals 1. Now, if tangent of theta equals 1, notice that's positive. And if that's positive, are we going to be in quadrant 1 or in quadrant 4? We're going to be in quadrant 1. Everything's positive in quadrant 1. So if we are in quadrant 1 and our tangent is equal to 1, theta must be what? Say it louder, sorry. I heard 0 and then what? 45. Yeah, it's going to be 45 degrees, or pi/4. The way that we know that is because tangent, we have to look at the different values of our x's and our y's to compute that out. Think back all the way to the beginning where we talked about tangent in terms of x's and y's, or tangent in terms of sine and cosine, because that will help you then to compute that. Tangent is what over what in terms of sine and cosine? Right, it's sine over cosine. So that means we need, if we're trying to get our tangent to be 1, then our sine has to be the exact same as our cosine. And the only time that that happens in quadrant 1 is at 45 degrees. Questions on that one? You can see the process that we're going through on this. Okay, let's look at tangent equals secant inverse, or arcsecant, of 2. So this is one we didn't play around with at all last time. So if we look at our notes page, secant, or inverse secant, is right here in the middle of the 3, right here towards the bottom. Notice our limitations are between 0 and pi. And it cannot equal pi/2. See, we have an asymptote there that we cannot equal. So I'm going to write that in terms of my theta, just so I kind of keep that in the front of my mind of where I'm going to be looking for my theta. Theta cannot be pi/2. So if we are lying between 0 and pi, if we're thinking about the unit circle, 0 and pi is the top part of our unit circle. 0 pi. So if we're thinking about the top part of our circle, that means it could be quadrant 1 or it could be quadrant 2, right? But what is secant in terms of like sine and cosine? 1 over cosine. So 1 over cosine, is that going to be positive, bless you, in quadrant 1 or quadrant 2? Are the x values positive on our unit circle in quadrant 1 or quadrant 2? 1. Everything's positive in 1. So once again, we are going to fall in quadrant 1. And we know that we want it to be positive because it says secant of positive 2. These are the mental steps that we're kind of taking. So we know we're going to be in quadrant 1, and we're going to do the exact same thing we did up here with our tangent, our arctangent. We're going to rewrite our secant inverse in terms of regular secant, where we have secant theta equals 2. And you've already told me that secant theta is 1 over cosine theta. Now, I don't really like this 1 over cosine theta equals 2, because if I look at my unit circle, I don't have a 2 anywhere. So if I multiplied the cosine over and divided by 2, what I'm actually saying is I have 1/2 equals cosine, just by manipulating the equation around a little bit. So I'm looking in quadrant 1, and I'm looking where is my x value equal to 1/2. 60 degrees. That's right. You can always check yourself by typing these into your calculator. Now, some of you might be looking at your calculator, if you have your calculator out, and being like, well, I don't have a secant inverse. And you would be correct. You don't have a secant inverse. But you can write secant in terms of cosine. And so you can note these different things for secant inverse, cosecant inverse, and cotangent inverse. And I can zoom in a little bit further on those. That secant inverse of x is the same thing as saying cosine inverse of 1 over x. Cosecant inverse is the same thing as saying sine inverse of 1 over x. And cotangent is the exact same thing. The only issue that we have with cotangent is that we have to say, like, for this part, we can do it just like the others, but that's only if x is greater than 0. If x is negative than 0, then we're going to add 180 to do a coterminal association with it so that it does still lie nicely for us. So these are not on the handout sheet that I gave you, so you might want to write them on there. These are mostly so you understand how to type them into your calculator, or how we're going to do some of these changes as we solve some of these equations in just a few minutes. So the only one that doesn't totally play nice is cotangent. And when you're finding the values of your thetas, that table that's at the bottom of the handout is also a really nice reference point, because it tells you on the far right-hand side what quadrants you can be thinking about. ready to move on? Okay. We're going to do some evaluations. And these are specific in that they state not to use a calculator. Again, I know on the My Math Lab, you're able to type this bad boy into your calculator and get an answer out. Again, I highly suggest using that as a check, not as a completion tool, because then when it comes to the exam, you're not going to know how to do any of the work to get the credit for the exam. And these do require a little bit more work because we are actually going to draw pictures with every single one of these. We're going to have to draw our angles to figure out our triangles. Like, we're going to go all the way back to like chapter 1, chapter 2 material in order to complete these. So for this evaluation, we have sine of our tangent inverse of 3/2. So that's a whole heck of a lot of stuff. So what I'm going to tell you to do is let's consider what's inside first. We're going to figure this part out, and then we will apply the sine to it. So we're going to call all of this in here, we're going to call it theta, so that then we're taking the sine of theta once we figure out what that theta actually is. So theta equals the tangent inverse of 3/2. So if we rewrite that, like we have been, in terms of tangent, we're saying we have tangent of 3/2 equals theta. Tangent, remember, fell into quadrants 1 and quadrants 4, so just as a note, we know we're going to be lying in quadrant 1 because we are positive. Tangent of 3/2. Yes. Thank you. Tangent of theta equals 3/2. Thanks for keeping me honest. Now, in terms of like all the way back, chapter 1, tangent is what over what in terms of x, y, and r? And I mean, that's a long way back, I know. It is y over x. So here's why we need to figure this out. Because we're going to have to take the sine of whatever this tangent of theta is, that's 3/2. So we're going to draw a picture like we did back in chapter 1 or chapter 2, where we have our different quadrants and we're going to draw our triangle. And we know we're in quadrant 1, so I'm going to draw it in quadrant 1. Okay? I'm going to draw my angle in here, where we have theta right here. And if we know that tangent is y over x, then my y is 3, and my x is 2. And what we don't know is we don't know what our r is. And the reason why we have to figure all this out is because sine is what in terms of x's, r's, and y's? Yeah, it's y over r. But we don't know what r is, so we got to figure it out. How do we figure out what r is? Pythagorean theorem. That's exactly right. We're going to have x squared plus y squared equals r squared. 4 plus 9 equals r squared. Square root of 13 equals r. So now, over here, I have sine theta equals y over r. Y is 3 over r, which is the square root of 13. We need to rationalize our denominator. 3 square roots of 13 all over 13. Another reason why it's good to know how to do this without a calculator is because some of you might not know how to type or get this type of answer out of your calculator, where it keeps it with a radical. It didn't want a decimal. because I don't know many people who can just randomly have decimals without a calculator. For these evaluation problems without a calculator, you will always end up drawing some sort of a reference angle over here and figuring out all your sides of your triangle so that you can use that information to get all the information that you need to solve. So we used the arctangent, we translated it into tangent, we drew it, found our missing side, and then realized we were taking the sine of that, and so then we were able to use that information. This is a really good section to help us dust off some of those cobwebs from the beginning of the semester and to show you that the stuff really does build on itself all semester long. Are there questions on how we did this one? Okay, let's do another one. All of these are going to work very similarly. We have tangent of the cosine inverse of -5/13. Again, whatever is inside, that's what we're going to let theta be. So that we're just finding tangent of theta. So we're going to let all of this be theta. When we talk about cosine inverse, we're talking about quadrants 1 and 2, but we're taking cosine inverse of negative. So we're going to specifically be talking about quadrant 2 this time. And we're going to have cosine of theta then equals -5/13. And cosine is what over what in terms of x, y, and r? X over r. And if we're in quadrant 2, I'm going to draw my triangle in quadrant 2. So if cosine is x over r, my x is -5, which it better be because I went to the left. I'm in quadrant 2. And then my r in this case is 13, and what I'm missing is my y. So I'm going to do the Pythagorean theorem. -5 squared plus y squared equals 13 squared. Not r, 13 squared. 25. And you can't see that, but it says y equals 12. This one was really nice. This is actually a special kind of right triangle, a 5, 12, 13 triangle. And again, we pick what our x's and y's or our r's are, like in terms of the signage, based on which quadrant we're in. Because taking the square root of 144 theoretically gives you both answers, -12 and +12, but I know I need it to be positive because I'm in quadrant 2. So I've made my triangle, I found all my signs, so then I'm going to come over here and think about, I'm taking tangent of this theta, whatever this theta is. And tangent, as you've already told me, is y over x. Well, we found that my y is 12 and my x is -5, so I have -12/5. Do we have any questions on the steps or the processes that we're using here? Because it's going to get more complicated, as it always does. Obviously, you want to be able to swing. Because I told you it would be nice to have out your identities paper and we haven't used our identities paper yet, so that's telling you that our identities are going to come up in the next couple of problems. Because here we were taking tangent of our inverse, or we took sine of our inverse, and so we only had to make one reference triangle because we only had one theta we were dealing with. But what happens if what's inside, if there's more than one bit? This one's obviously more complicated because we're not just taking cosine of arctangent, we're taking cosine of arctangent plus arcsine. There's two different bits and pieces in here. And hopefully just looking at it, even before we do anything with the arctangent, arcsine aspect of it, you notice that we have cosine of something plus something else. And so that hopefully that's immediately jogging your brain a little bit about the cosine of a sum and difference identities that we talked about in Chapter 5. Because here we are taking the cosine of a sum. And so that's probably going to come up to play here as we start working through this. Now, on the previous examples, we just had one theta in terms of what was inside. But here, because we have this plus, we really are dealing with two different things. We have our arctangent and we have our arcsine. So instead of calling them theta because they're not the same thing, we're going to call them A and B. Just a way for us to differentiate them. So we're saying A equals the arctangent of radical 3, and we're saying B equals the arcsine of 1/3. Now these are totally different expressions, so we're going to have two different triangles that we are going to play with here. So I'm going to deal with my arctangent, and then when I'm done with my arctangent information, I'll come over here and do my arcsine. I don't want to do them back to back and get confusing here. So if I have A equals the arctangent of radical 3, how can I write that in terms of regular tangent? What will that translate over to? Yeah, tangent of A equals radical 3. Great. So I need to draw a triangle based on that information. And you're like, well, that's not a lot of information. You're not wrong on that. It's not a lot of information. But I know tangents in quad 1 or quad 4. Since it's positive, I'm in quad 1. And I know that tangent is what over what again? Y over x. So if this is y over x, you're like, well, wait, there's nothing in the bottom. Well, we can make it over 1. So we have a y over x. Where we have radical 3 as our y, and we have x is 1. And we are going to figure out what our r is by taking 1 squared, which is 1, plus radical 3 squared, which is 3, equals r squared. So 4 equals r squared, so 2 equals r. And then we're going to leave that alone for a minute, and we're going to go play around with our arcsine of 1/3 and do the exact same process. Because if b equals the arcsine of 1/3, then I can write that in terms of sine, and what will it say? Sine of b equals 1/3, exactly. Now sine deals with quad 1 and quad 4. Since it's positive, we're going to be in quad 1 again. And sine is y over r. So it'll be 1 over 3. And we need to figure out what our x is. X squared plus y squared, which is 1, equals r squared, which is 9. Subtract that. Take the square root of both sides. And we find that x is 2 square roots of 2. And you're like, okay, so why in the world did we do all this? Well, what we did is we've made our triangle so that we have our reference information. Because what we're doing is we're finding cosine of A plus B. That's, in essence, what we're doing up here at the top. Since we're letting all of the arctangent stuff be A, all of the arcsine stuff be B, we have cosine of A plus B. But from the last chapter, which you can't see that, from the last chapter, cosine of A plus B is our cosine of sums. And our cosine of sums states that we have cosine of A, cosine of B, minus sine A, sine B. And so we had to come up with these triangles because we can't find the cosine of A based on the arctangent if we don't have the triangle to go figure out what the cosine of A is. And we can't find the sine of A. And we couldn't find the sine of B or the cosine of B in the same way. So now we need to figure out all of these values so that we can figure out what cosine of A plus B is. So everything that's A on mine, at least, is blue. So this is blue. And blue, and then, I know if you're color blind, I'm sorry, green, blue and green are probably not two to have back-to-back like that. So cosine of A, cosine of this left triangle in terms of x and r. Cosine is going to be x over r. So if I'm looking at this left triangle and thinking about x over r, what is it? Yeah, 1 over 2. Then I'm going to switch over to this triangle, and I'm going to do the same thing. I need to find cosine of b. So again, it's still going to be x over r, which is 2 square roots of 2 all over 3. Then a minus, and then I'm going to go over to this left triangle, and I'm going to figure out what sine is. Sine is y over r. Radical 3 over 2. Then I'm going to come to the right triangle and do the same thing. And now I'm going to do algebra, and I'm going to combine all that. Notice that I'm going to have a denominator of 6 for both of these fractions. So I'm going to have 2 radical 2 minus radical 3 all over 6. Now, could you leave it separated? I don't see why not. If you wanted to have it radical 2 over 3 minus radical 3 over 6, that would be fine as well. I would play around with it in my math lab to see if they prefer it separated to where it would be radical 2 over 3 minus radical 3 over 6 like this, or if they prefer it combined. I don't think it matters. For me, on a test, it wouldn't matter. So this one, we had to do the same stuff and the same steps that we did on the previous problems. We just had to do it twice because we were dealing with 2 different arc inverse trigonometric functions. And then we had to go back and remember or look up our identity here for the sum of cosines. Are there questions? Okay, we're going to do one more. One more problem. Are we good for me to take this one off? Okay. this one, we only have one term inside. So we won't have to do the double triangles that we just did in terms of having a triangle over here and a triangle over here. But we do have to be able to look at it and say, okay, we have tangent of 2 arc sine of 2 over 5. So what kind of identity do you think we're going to end up using at some point? Do what? Yeah, that's a good guess. That's a really good guess. Because here we had cosine of something plus something, and we used our sum of cosines identity. And here we have tangent of 2 times something. And in the previous section, those were our double angle identities. So that is where I would go to. So double angle with tangent. Luckily, there's only one of them, which is nice. So we are going to do a similar thing. Since I'm going to use the double angle identity, I'm not going to include the 2 in my B. I'm going to just let this stuff be my B, or theta, or A, or whatever you want to call it. Okay? But I'm going to say B is arc sine of 2/5. And then I'm going to turn that around so that I can have sine of B is 2/5. So I'm going to fall in which quadrant? Huh? Yeah, we're going to fall in quadrant 1. Sine's positive. We're going to fall in quadrant 1. So there's my triangle. Sine is y over r. So that's 2 over 5. And I'm going to have to figure out what my x is. So x squared plus y squared equals r squared. Subtract that 4. Square root both sides, and we get radical 21. Now, I can go ahead if I really wanted to, and I could figure out my tangent of B and shove that in over there, but I'm not going to do that just yet. Because if I look at my double angle identity, it's kind of got a lot of stuff going on. So I'm going to look at it just by that. Because right here what I have is I have tangent of 2b. If I'm saying b equals all this jazz, then I can say tangent of 2b. So tangent of 2b then, or not 2b, no, that's lame. If we look at our double angle identity, then I can write this as 2 times tangent b over 1 minus tangent squared b. So if I'm looking at the identity, then the only thing I need to figure out then is what is tangent of b. And I can do that from my triangle over here. Because tangent of b is going to be what over what? X, Y, R, what over what? Huh? Y over X. So it's 2 over square roots of 21. Got to rationalize that denominator. And you can't see that. There it is. So tangent of B becomes 2 radical 21 all over 21. Now I'm going to put that in everywhere over here that my identity says tangent of B. And then obviously tangent of B is going to be squared on the bottom. 2 times 2 radical 21 over 21 on top, 21. And then on bottom, I have 1 minus 2 radical 21 over 21 squared. So we got fractions and fractions, we got radicals, we got all kinds of fun stuff. On top, I'm going to have 4 square roots of 21 all over 21. On bottom, I'm going to have, if if I square this, notice I'm going to need to combine this at some point. So I'm going to have 21 over 21. Then over here I would have, oh man, are my notes wrong? Oh, I know what I did. I'm going to keep going the way that I am, but I know what I did. 4 times 21 over, what's 21 squared? Okay, can I show you what I did in my notes so that it makes it a little bit easier? Because 21 squared is gross. So whenever I plugged in right here, I plugged in 2 radical 21 over 21 for the top. I didn't put in the bottom in my notes, I went back up and put this before I had rationalized it, because then when I square it, what happens to the bottom? The radical goes away and it automatically gets rationalized without me having to take 21 times 21 and get all gross. So I kind of recommend doing that. There's nothing wrong with doing it with the already rationalized one, except that you can see it's going to get really gross. Whereas if I leave it like this, then all that happens is I end up with 4 over 21, which is much nicer, more user-friendly. Don't have to take 21 squared or do any of that. So you get 4 radical 21 over 21. That's the top. And then on bottom, I'm going to pop it around so that I can go ahead and start simplifying it, because I'm going to have 21 over 21 minus 14, or 4 is 17. The 21s cancel, leaving me with 4 radical 21 all over 17. So in general, you do want to always make sure that you do have a rationalized denominator, but sometimes if you're plugging it into something that's going to be squared, leaving it unrationalized, at least for that one, will make your algebra a lot easier, because when you square a square root, it's going to get rationalized anyways. You don't have to worry about that denominator. We could have followed through with what I had written here, though, where we had the 21 squared. It gets very large. And then obviously you do have to use a calculator. Notice that on all of these problems, not one single time did we actually need a calculator. And that's kind of the point. I think you should have a calculator to check your answer if you know how to get answers like this out. And if you don't know how to get answers like this out, then what you can do is you can type in the answer that you get and get the decimal equivalency, and then type in the original and make sure that your equivalencies do match up. But on none of these problems did we actually use a calculator at all today. And they're pretty complicated problems. So if you start going down a path kind of like we did here, where I'm like, well, crap, I need to know what 21 times 21 is, maybe that's a good sign that there might have been a slightly simpler way to do it. That doesn't mean the way that you're doing it is wrong necessarily.